So in this video we're going to show that the equation of motion of an object thrown under the force of gravity is a parabolic trajectory. So imagine we're standing at point A and we just throw a ball. It'll go up in the air and it'll land at point B. So as soon as it's left your hand, it stops accelerating in the X direction, and the only acceleration is in the Y direction due to gravity. So again, we're going to solve this using calculus of variations. So we'll split this into one single little element, and we'll do the analysis on that one element, and then we can add it all up at the end to get a final value. So if we take a small element ds, if at any point in time this was just left to fly off without any action of gravity, it would travel in this direction here with a velocity of v. Also, we know that the gravity is a conserved force, so we can use this value here. We know that the kinetic energy plus potential energy is a constant, so we can say then that the action that we're interested in is just simply given by the kinetic energy. We've seen this derived in a previous video, so we can say then that we're interested in twice the integral of the kinetic energy with respect to time, and we know that this is the component that is actually stationary. So we've seen that whenever we looked at the ideas of least action in a previous video, but we will get into that again in more detail in later sections. So what we're interested in is the kinetic energy. So kinetic energy is given by a half mv squared. So, but we know the velocity here is equivalent to this little segment here, the rate of change of this segment with respect to time. So it's going to be our ds by dt. So therefore we can say that our small change in our segment ds is equal to v dt. So putting these into our equation for the stationary action, we're going to have 2 times the integral of the kinetic energy, which is a half mv squared, by dt. So that can be written as the value of the 2.5 cancel, so we just have an mv squared by dt. And if we say that the value of m is just equal 1, so let's say the mass is just a constant value of 1, then we can take that out of this equation and we're just left with the v squared dt. But we can see here that the value here of v dt is equal to our ds. So we've got one of these v dt's, so we're left with, will give us a ds, and we'll be left with one other v. So this is going to be the integral of v ds. So this is what we're interested in here, and we have to go and find the ds and the v. Now the ds, we've done this before several times. We can say that ds squared is dx squared plus dy squared. So therefore we take out down the dx squared down, and then find the square root, and then take the value of dx back up. Then we'll have our ds equals 1 plus y derived to the square to the power of a half times dx. So I've seen that quite a few times, and it appears all the time, with lots of times within our examples in the calculus of variations. So what about the value of v? Well, with a little bit of physics, we can say that the velocity squared is the initial velocity times 2 times the acceleration times the distance travelled. Again, I'm not going to go and prove these things, okay? So that's a kind of high school physics. So I could maybe put something in the section at the back, maybe an appendix at the back, okay? So in fact, I'll put that in appendix at the back, and you can go and have a look at that derivation. So we can have then our v squared is going to equal a u squared. Now what we've got, our distance s, well our distance s is just really a function of the height is a function of the distance x, that's just a function y of x. And our value here for our acceleration, well it's acceleration under gravity, but of course the positive direction is up here, so we are actually moving down the way in this direction, so we're going to have a minus sign, so it's going to be minus the value of g. We've got our factor of 2 there, so that can really be written as v squared equals u squared minus 2gy. So when we put these two into this equation up here, we're just going to be left with the integral of the first part here, which is our u squared minus 2gy. So it's going to be u squared minus 2gy, but of course it's going to have to be to the power of a half, because this is in terms of v squared. Okay, so it's in terms of v squared, and we only want it in terms of v. And then the other part is 1 plus y derived to the square to the power of a half by dx. Now this is our functional here that's going to get provide a minimum value, or if we're going to find an extremum for it. And if we're interested in the fact that the function here has got independent variable x, but the things that depend on x are going to be the y and the y derivative. So again, we can simplify the Euler-Lagrange by using the Beltrami identity. So what we're interested in finding is f minus y derivative of partial f by partial y derivative equals a constant, using this function here which we have just derived. So let's go ahead and we'll do that just now. So we take our function f, so that's it just written there, and we take away y derivative times the derivative of the function here with respect to y derivative. So that's going to be, well, there's no y derivative term in this, so that just remains as is. But there's a y derivative term in this one here, so we differentiate this section here, so it's going to be a half of 1 plus y derivative squared to the power of minus a half times, when we differentiate what's inside that, it's going to be 2y derivative equals a constant. So now what I'll do is to simplify it out, I'll write this term a as this term here, and the term b is this term here, and that's going to be minus y derivative of, and we're going to have the first term here which is a term a, and we're going to have the value of our 2y derivative which will remain the same, I'll just leave it there, and the term in the bottom is going to be a factor of 2, and it will be the value of b. So this term here is to the power of minus, so when you put that underneath it becomes to the power of plus a half, so this term would be the same as this here. Okay, so that's be 1 upon 2b. You could actually cancel out the 2's there, I don't know why I left them in, but it doesn't matter, we'll just continue as is. So that is a times b minus, well, the y derivative multiplies the y derivative, so you get a 2y derivative squared, and this term here becomes our a upon 2b is equal to a constant c. So we can take here a common denominator of 2b, so we do that, we end up with 2ab squared minus 2y derivative squared times a. So that's the same as ab squared minus y derivative squared times a upon b, so just cancelled out the 2's there. And so we take a common factor of a, and we have b squared minus y derivative squared all upon 1 plus y derivative squared to the power of a half. So we'll put our terms back in. Our a is this term here, and our b squared is going to be given by our 1 plus y derivative squared. And then we can take off our minus y derivative squared, and it's just going to be left with this term here, u squared minus 2gy to the power of half upon 1 plus y derivative squared to the power of a half is equal to a constant. Now I'm not going to work through the derivation here because it's just a lot more mathematics and bookwork, so you can have a go with this one yourself if you like, but what you've got to do is got to put it in terms of the y derivative, and then so this is to be transposed in terms of y derivative, and then you have to solve the little differential equation using a substitution in order to get a final function. Now the final function is this one here. So you can see this here just gives you the equation of a parabola, because the value d is a constant, the value g is a constant. So this is really, on this side here, it's just like ax squared. And on this side here, the c is constant, the g is a constant, the u is a constant as well. So all your reference really is the y on this side. So you've got really y equals ax squared, which is a parabola. And you'll see that in the graphical calculator. So let's go now, we'll have a look at this in the graphical calculator, and you can see what each of these terms are and what they do and what they mean. So this is the equation that we derived, which is a general equation for a parabolic trajectory of an object thrown under the force of gravity. So we can see here that the value of u is the initial starting velocity, so that's the velocity that you throw it, so in effect the velocity in, say, from this point here in this direction. So you can see that there, if we adjust u, then it moves this curve up and down, and that makes sense because if we were in this position here, starting at this point, and we threw it a certain velocity, it would go that distance. So if we were to increase the velocity that we was the starting velocity, then the distance that it travelled would be increased. If we kept the angle exactly the same, we just get a different finishing point. So that makes sense for that. So now I've set that up to a value of 10. So we're throwing that initial velocity of 10. Okay, so the value d here, well, this value d is just your starting position, so it just adjusts where you're actually standing whenever you throw the ball. So we'll set that back to this value here. In this instance here, it's sitting at 5.1. okay, just put it at 5.1 because it makes it work out here as this point here being the origin. Okay, so that's the initial position. We've got gravity, which is 9.81, and also this value c is going to give us the angle at which we throw the ball. So in order to test this out and see that this actually works, then what we could do is we want to set the angle. So that's the angle there at actually 45 degrees. Now if the angle that we throw it at is 45 degrees, that's going to give us the maximum distance that it should travel. And that maximum distance is going to be given by the velocity squared over divided by the gravity. Okay, so the velocity squared in this case here, it's going to be our initial velocity is 10, so it's going to be 100 squared upon 9.81, which should be a value of 10.2. So if this is correct and this equation is right, then we should get a value of 10.2 whenever that is it's sitting at 45 degrees, and that's a check on it there. You can see that we're getting 10.197. So this indeed is the graph that we're looking for, and this is a graph of a parabolic trajectory of a ball thrown under the force of gravity. So that's I've left a copy of this in the resources section, so you can go and download and have a little play with this if you want. But that's all there is for this video. I'll get you on the next video. Goodbye.